voice. And okay, YouTube is starting to record. OBS is here, and I'm going to share the screen now. There we go. All right. So the screen is being shared. I will go ahead and get today's class started. Okay, I'm almost done grading all the questions. I got 3 more people to grade, and this time the grading approach is a little bit different compared to the first exam, because it doesn't make sense for me to grade the same question, for everybody, and then switch to another question. So this time I'm grading person by person. I got 3 more people to go. If you go to the share document, you can find my comments next to your question. So that's the feedback. There are no point values yet. So so that is for a little bit later, because I want to see how the class overall did in a particular question before I can set up a standard of what would be considered as a B, C, D, F in terms of the quality of the answer. All right, so I'm gonna paste the recording link in today's lecture so that people who want to watch it again can find it over here. And then we'll go ahead and continue to talk about the A-star algorithm. So are there any questions from last week? Did anyone, did anything over the weekend, such as writing Dijkstra's algorithm out in, just writing the program out and give it a try, see if it works, that sort of stuff. Did anyone give it a try? I'm guessing no. Nobody responded to that question. All right. So I do know that it is a little bit of extra work to write Dijkstra's algorithm, but nonetheless, it is a good exercise to do. The implementation doesn't have to be using strictly the way we implement set and functions. But it's still a good idea to write that algorithm. C++, Java, JavaScript, those are all programming languages that are suitable for this type of programming. All right, so without any further questions, I am going to go back into the notes of graphs, and this time we'll go ahead and kind of track down the A-star algorithm and figure out how it works. Okay, so the A-star algorithm is a little bit longer. It is a little bit more complicated. And that's mostly because the A-star algorithm makes use of a heuristic function that we call H in the algorithm. So what we'll do today, last time we talked about all these terms here. Specifically, we also talked about what is H doing in this algorithm. It is basically a very easy to compute function. Typically, it's a constant time type of computation, so that we can quickly figure out an estimate of the length of the shortest path between 2 vertices. So the idea of H is it is just an estimate. It is really fast to compute, and it never ever overestimates. Okay, so that's one requirement of H. We are still maintaining that all the edges, none of the distance of edges should go negative. And the heuristic value should not go negative either, because if we know ahead of time no edges has a distance that is negative, we also know that the length of any path cannot go negative either. So those are the basic assumptions of the algorithm. So what we'll do today is we're going to get started with the initialization. So this loop over here, the for each loop, is basically an initialization. And we'll go ahead and take a look at what it is doing in the initialization. So the first part is we just take any v, the lowercase v, which is a vertex from the set V, the uppercase V, and then we just look at this particular vertex v and then decide what to do with it. If v is not s, okay, so in this case s is the start vertex, so s lowercase s is what we call the start vertex, then we perform these initialization. Otherwise, for the start vertex alone, we perform these initialization in the else branch. So let's go take a look at what if we are not dealing with the start vertex. What are we initializing? So we're initializing g of v to be infinity. We're also initializing f of v to be in infinity. So it is important to understand what is g and what is f. So g in this case is the actual length of the shortest path from the start vertex s from the short. Okay, it is the actual length of the shortest path from the start vertex s to vertex v here. Okay, it is the actual. But if we are at the very beginning of the algorithm, because we haven't really explored any edges, so we just make this infinity to basically say, okay, in the worst case, we assume that there is no path between this vertex v and the start vertex, and therefore the length of the shortest path is infinity. So now we look at the meaning of f. Okay, f of v is the estimate of the length of the shortest path from s through v to the destination x. So x is the destination because it is stated here. Let x in v be a destination vertex. So let's go ahead and take a look at a picture, because I think at this point a picture is going to be helpful to show you, what what g is, what f is, and what h is. Okay, so we'll go ahead and open up Zerno, and then we'll take a look at an example. Well, it's not so much an example, but it's more of a schematic to display, how those functions are related. All right, there we go. Okay, so with the A star algorithm, you can only have one single start vertex S, and you can only have one destination vertex X all the way over here. So for all the vertices, there are not S nor X. Okay, so we have let's say we have vertex V here. Okay, let's just say that this is in the middle of running the algorithm, and we have explored enough edges to find a path from vertex S to vertex V. In other words, this is already explored. Okay, there is a path from S to V, and this is not a single edge. Okay, we are not talking about a single edge, which the path can boil down to a single edge, but it is not. Okay, it's just a general path over here. So the length of the current shortest path between S and V is known as g of V. S is not a part of the parameters because we only have one single start vertex to begin with, so it's not a big deal. Okay. Now, what is f of V? So f of V is to combine g of V with the heuristic going from V, vertex V, to vertex X. Okay. Let me back up a little bit here because I want to use a different color to show you, to differentiate between, an actual known length versus a guesstimate. Okay, so let me just back up a little bit here and use, I'm going to use green, light green, to represent a heuristic or just an estimate here. Okay, so this is what we know as h of v to x. All right. So the way we compute f is actually pretty simple. Okay, the way f really boils down to is f of v is g of v plus the heuristic going from v to x. In other words, f of v combines, a portion of it is exact. We actually know that the current known shortest path from the start vertex to vertex v is g of v. Okay, so that part is concrete. We know, that the actual shortest path cannot have a length that is more than g of v. Okay, but it doesn't go all the way to the destination vertex x. Okay, but it also combines an estimated portion, which is h of vx, because that is just an estimate from vertex v to get to the destination vertex. So f of v is basically an estimate of the length of the path going from the start vertex through vertex v and then go all the way to vertex x. Okay, it is an estimate of the full path through v to the destination. Do we have any questions about what is g of v and what is f of v and how f is expressed by g and h? So I'm gonna let you guys have a moment to.
I'm
Yeah.
sorry. Is V the destination vertex in this case, or is it X?
Okay, so I'm using the same terminology as the algorithm itself. So x is the destination, s is the start vertex, and v is just basically anything other than x or s in general.
Okay, thank you.
All right. So just like last time, just like last Wednesday, it is going to be helpful for you guys to open up module 0310, which is what you're seeing here in the browser, and just put it on the side. Okay, you put it next to the live stream screen. So this way, when we're looking at the graph, when we're looking at the tablet, my tablet screen, you can still look at the algorithm independently on the side. Okay, so try to do that if you can. Okay. If you guys need a little bit of time to set it up, just let me know, and I can just kind of pause for maybe like 30 seconds or 60 seconds, so you guys have a chance to do it. In fact, to make it slightly easier, I am going to copy and paste the link. Oh, thank you, Brenda. We had the same idea. So this way it's easier for you to open it from inside Discord. Obviously, this may not work very well if you're using a phone right now, because most phones can only display one screen at a time, and if you split a screen that is only about 5 or 6 inches diagonally, that may not give you enough area to actually view the content. All right, so I'm not hearing anyone needing more time, so I will continue to talk about the algorithm. Okay, so now that we understand what is g of v and what is f of v, okay, so the initialization, it'll kind of make sense. Okay, so let me switch back to the tablet view over here. When we are at the very beginning of the algorithm, okay, let me use red to highlight what is not known yet. Okay, so when at the very beginning of the algorithm, this path is not known yet. In other words, we just know that the start vertex is s, there's a vertex v, and I have no idea whether those are even connected or not. Is there a way to go from the start vertex s to the vertex v? I don't even know. Okay, so that's why the initialization is saying, let's just call that infinity. In other words, let's just say that there is no path right now going from vertex s, the start vertex, to vertex v, because that's a reasonable assumption, because we really don't know whether there is a path connecting these two vertices or not. Okay, so going back to the algorithm, and that is why g of v is initialized to infinity. Now, on the other hand, okay, let's talk about f of v. So you can see f of v is g of v plus the heuristic going from v to x. Now we know the heuristic going from v to x is probably an underestimate. It can be exact, okay, but it's probably just an underestimate. But since g of v itself is infinity, infinity plus whatever is always going to be infinity. And as a result of that, f of v is initialized to infinity as well, because g of v itself is infinity. So do we have any questions about the then branch of the loop that is really just a part of the initialization of the algorithm? No questions? All right. So now the question is, what if V and S are the same thing? In other words, we are just looking at the start vertex. The start vertex has a G value that is 0. Okay, so does that make sense? So switching back to the tablet, okay, so basically we are saying, S and V are really the same thing. Okay, so they're the same vertex. Remember the definition of G of V. Okay, the definition of G of V is the length of the shortest path going from the start vertex to vertex V. Well, what if V and S are exactly the same thing? What is the shortest path going from the start vertex to the start vertex? Well, the length is going to be 0, right? We don't even need to traverse a single edge. We are already there. So that's why G of V is initialized to 0 when when V and S are exactly the same thing. What about f of the start vertex? F of the start vertex is G of the start vertex plus the heuristic of from the start vertex to the destination vertex. Okay, but we already know the G of S is 0, so that's why it boils down to just the heuristic going from the start vertex to the destination vertex, and that is how we initialize it in the algorithm right here. So do we have any questions about how the G and the F values are initialized before we run the main loop of the A-star algorithm? These are really just for initializations. It's done one shot and we're done. We're good. No questions? All right. So the next one is more confusing. We're basically keeping track of how did we get to vertex V. That's what prev is for, okay? It's previous. So the previous of a vertex V, they're all initialized to undefined. In other words, we are going to make these not undefined later on in the algorithm, but right now they're all defined to be undefined. I know that sounds kind of like an oxymoron. We are defining something, we are assigning the undefined value to the previous of V for all vertices. But that kind of makes sense too, because we haven't explored a single edge. If we have not explored a single edge, how is it possible for me to determine how I can get to a particular vertex? Which edge can lead to a particular vertex? It doesn't make sense, right? So that's why they're all initialized to undefined. Unlike Dijkstra's algorithm, which makes use of E prime, which is a set of edges to keep track of the solution graph, the A-star algorithm relies on basically back pointers, which are the previous values of a particular vertex, so that when the algorithm is done, we can track the shortest path from the destination and keep backtracking using the previous to go all the way back to the start vertex. That is how we find the shortest path when the algorithm is done. All right. So let's see whether there are questions or not. Okay, so there are no questions. All right, so moving on to the next line of the initialization. This time we are initializing a set O, which sort of kind of works the same way as the set Q in Dijkstra's algorithm. Okay, so O is a set and it is initialized to just the start vertex. Now this is very different, okay, in a way compared to Dijkstra's algorithm, because Dijkstra's algorithm starts with all the destination vertices, but in the A-star algorithm we start with the single one only start vertex. Okay. All right. So do we have any questions at this point about the initialization of the A-star algorithm? Okay, so no questions. All right. So now that we have everything initialized, the main loop of A-star algorithm goes from here, and this is the entire loop here. so let's go ahead and take a look at the loop itself. So we'll analyze the structure of the algorithm first, and then we'll go ahead and, just like what we did with Dijkstra's algorithm, we're going to run a few examples through this particular algorithm, just so that we have a little bit of hands-on exercise on this algorithm. Okay, so but we first have to understand what each line is doing before we can actually trace the code. So we'll go ahead and take a look at this here and ask, what is this doing here? So the while condition is not quite as simple as Dijkstra's algorithm. Dijkstra's algorithm basically just says, as long as Q is not empty, keep doing this. But the while loop of the A* algorithm is a little bit different. It basically says, as long as I can find a single vertex in O such that f of v is less than g of x, then we keep doing stuff. Okay, we continue to go through, then we go through another iteration of the while loop. Okay, so now the question is, now this is existential. In other words, we just need one single vertex in O that satisfies this requirement in order to perform another iteration. But what does it mean? What does this mean? Okay, in other words, let me highlight this portion here. Okay, so what does that mean? Okay, we got f of v, we got g of x. What are they? What is the value? What are the meanings of these values? Okay, we'll start with this one. Okay, what do you think is the meaning of g of x? What is the meaning of the g function in general? We talked about this a little bit earlier, and in the graph, we kind of talked about it like this. Okay, so let me scroll down here. Okay, and just kind of mention the whole thing again. So we have a start vertex. We have a destination vertex. We have a vertex v, which usually is not the start nor the destination vertex. We have partially explored the graph, and we found a path. Okay, this solid black line is one path going from the start vertex s to the vertex v over here, and the length of this path here is g of v. In other words, g of v is really just the length of the shortest known path from the start vertex to vertex v. Okay, so what is g of x then? What is the meaning of g of x? Well, g of x is really defined kind of the same way. Okay, we have some kind of a path going from the start vertex to the destination vertex. Okay, and g of x is really the length. Yes, it was initialized to infinity. Okay, but during the execution of the algorithm, at some point it may not be infinity anymore. So Carol, you are correct. G of x was initialized to infinity, but at some point it may not be infinity anymore, because as we explore more and more and more and more edges, we might actually find a path, not necessarily the shortest, but a path from the start vertex to the destination vertex. Okay, so g of x at some point is not going to be infinity. Instead, it is the length of the shortest known path from the start vertex to the destination vertex. So are we good so far in terms of the meaning of g of x? Is that okay? All right. Okay,
Sounds good to me.
Okay, good. So now let me go back to the algorithm. What are we comparing that thing to? We're comparing it to f of v. Okay. So the question now is, what v are we talking about? Okay. Well, v is just some random vertex that is just somewhere in the graph. Okay. And somehow it got into the set O. So now we have to take a look at it and go like, hey, do you have an f value that is less than the g value of x? Okay, but what is f of v? Okay, so f of v, using the same color scheme as last time, we have an estimation function here called hvx. Okay, and when you look at the definition of f of v, it really is just g of v plus h of vx. Okay, we got this previously already. In other words, f of v is a combination between what is the known length of the currently known shortest path from the start vertex to vertex v, and then we add the estimated portion, which is how far do you think we have to go from vertex v to the destination. So we're adding those two together. So after we add those two together, then we end up with an estimate. Okay, and this estimate is, if I start from the start vertex and I go through v, and then we go to the destination vertex, what do you think is a kind of an estimate of that particular, what is the estimate of the length of that particular path? That's what f of v is trying to tell us. Okay, so in other words, okay, if I were to use green here, f of v is this portion here. The dark green line is telling us, back. This is f of v, okay? And then the black line over here is g of x. So we are really comparing g of x, which is, this is the length of a path going from the start vertex to the destination vertex. And we're basically asking, do we have any hope of finding a shorter path, by exploring one of the vertices in O? That is what the while condition is asking. Do we understand that part? You might want to write it down too, or type it. Okay, so let me just repeat that, because I think this is super important, because the symbols can be confusing because they're very mechanical. But when you associate a meaning to an expression like this comparison, then it gets a little bit easier to understand. Okay, so this is a Boolean, which means it's either returning true or false. Okay, what it really is asking is there any vertex in O that potentially is in the middle of a shorter path than the path that I have already found from the start vertex to the destination vertex? Okay, this code just kind of crapped out. All right, so I think I'm back. Let me go back to this class. There we go. So I think I'm back. Okay, thank you for confirming everything is back to normal. Discord just crashed on me. Don't know exactly why, okay, but it did just crash on me. No, it would not have disrupted the YouTube feed. The YouTube feed is independent to Discord. This, in fact, it's the other way around. Yeah. Okay. Cool. All right. So I do apologize for the technical difficulty. Okay, but it should be all good now. All right. So getting back to here. So the condition here for the while is basically saying, if there is anything that looks kind of promising, that this may represent a through vertex to get to as a part of the actual shortest path, let's go ahead and continue with this algorithm. That's basically what it's saying. You can also look at this from the opposite perspective, which is basically saying it doesn't look like anything is going to it doesn't look like we can find a shorter path. Okay, so let's explore that perspective for a moment. Okay, so let's go back to this graph over here, and this time Uh-oh. I just misplaced my stylus. Where did it go? Uh-oh. I knew this would happen someday. Just give me a moment here to try to find my stylus. Huh. That is embarrassing. I was just using it a moment ago, and I suppose I can just use my mouse to draw some pictures, but it's not going to be as easy. All right, well, I'm not going to waste too much time to do it. Yes, the matrix. It's more like Murphy. It's more like Murphy doing his stuff here. Okay. So let's go ahead, and I can always type. Okay, this is one thing about Zernal is I can always just type. So I will just go ahead and type this, and you guys can tell me, what does it mean? Okay, if I say for every single vertex in the entire graph, okay, or at least in O, okay, for every v in O, f of v is greater than or equal to g of x. What does that mean? Okay, if this is true, so let me just kind of do the whole thing for all v in big O. Okay, this is true. What does it mean when that is true? Okay, that looks ugly, but it's good, close enough. Okay, so but what does it mean when this quantified statement is true? Okay, so I want you guys to think about this a little bit. You don't have to answer my question, but I do want you to think about it. What does it mean? F of v is the estimated length of a path going from the start vertex through v to the destination. G of x is the actual length of one path, okay, currently known as the shortest, from the start vertex to the destination vertex. So what does it mean when every single v in O has f of v greater than or equal to g of x? All right, so Carol is typing. Good, good. There's no shorter path, exactly. So, there basically no shorter path can exist anymore, because because g of v is always known to be, it cannot overestimate. Okay, it is at best it is exactly the same, and it would never overestimate. Okay, so that means if f of v is greater than or equal to g of x for every single v in O, then we are done. Okay, we have found the shortest path already at that time. Okay, so now let's go back to the algorithm. So the next statement resembles a little bit of what we do in Dijkstra's algorithm. So instead of using v as a variable, I'm using c as a variable. So here it says, let c be a vertex in the set O such that da 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 da. Okay, so can someone tell me what this whole thing is saying? The expression that is currently highlighted in the browser. It says for all w in O, f of c is less than or equal to f of w. What is that saying? And is the A star algorithm a greedy algorithm? Oh, I found my pen. Cool. So does anyone want to give this a try? What does it mean, in that particular statement? Okay. Well, it's a greedy algorithm. Okay, A star is a greedy algorithm. You can also call it an optimistic algorithm, because what it's doing here It's going through all the vertices in O, and it says, I'm going to try out the one that looks the most promising. That's what it's saying. Because the f value of a vertex, once again, is usually the estimated length of a shortest path from a start vertex through a particular vertex to the destination vertex. That's what the f value is saying. So all the f values really are estimates of path, of the length of path, through basically different options. Okay, Carol type here. So W is like an instance of C. No, W is it is bound to a vertex using the quantifier. In other words, W is a quote-unquote local variable. Okay, so let me explain what I mean by that. So W is a local variable within the context of the highlighted portion here, and that's all it does. Okay, it does not. We don't use W anywhere else. Okay, its scope is within that expression. So yes, Carol, you got that. Yep. Okay. So I'm basically just looking through all the vertices in O, and I'm asking which one of you looks the most promising to be on the shortest path, and let's just pick that one. Okay. So it is a greedy algorithm, okay, because this is what usually a greedy algorithm would do, is to just say, okay, which one looks the most promising? We'll explore that first, okay? The next statement also resembles something that we do in Dijkstra's algorithm. Once we pick something out from the set O, we remove it from the set O, okay? So this way, we do put things back into O, okay, because otherwise you can see that this while loop will only go one iteration, right? So we do put things back into the set O, okay, but once you pick something out of O and you say, oh, this vertex looks really promising, let's check it out, okay? So that is when you take the vertex out of O, when you decide to check it out, okay? So the next statement here, okay, the for each, looks a little bit like the for each loop as well in Dijkstra's algorithm, except this one is looking at the edges coming out of C and not the edges going into C. And that has to do with Dijkstra's algorithm start with the destination vertices, and A star starts with the start vertex. So the direction is exactly the opposite, okay? So we basically, if you look at this entire statement here, all it is saying is, let's check out every single outgoing edge coming out of vertex C, okay? All right, fine, what do we do with it? In this algorithm, I use a local variable t, so I'm computing g of c and the distance of the edge Cn, okay? Now remember, Cn is an outgoing edge from vertex C, so I'm basically just combining these two. So if t is less than g of n, guess what? We have just found a shorter path from the start vertex to vertex n. That's what it's saying, okay? So let's check this out, okay? Let's check out these two statements over here. This is just an assignment statement so that we have a temporary variable t, so I don't have to express the entire sum on the other side. Okay, but what exactly are we comparing? We are comparing g of c plus d of cn against g of n. That's what we're comparing. So what exactly does it mean? Okay, why are we doing this comparison? Why do we want to do that? G of c is the length of the shortest path to vertex C already. We know vertex C goes to vertex n because each neighbor n of v, right? It's right here. We know that C has an edge going to n. So we can get to vertex n through C. Okay, that's a known already. So when you add the distance of the edge Cn to g of c, the sum, which we know as local variable t over here, is the length of a path going through vertex C to get to vertex n, okay? The question is, well, is this path and is the length of this path shorter than what we might have known already about getting to vertex n. That is what we are asking. And that is why we are comparing t to g of n, because g of n is representing the length of the currently known shortest path from the start vertex to vertex n. Okay? So when t is less than n, that means, oh, guess what? We just found a shorter path from the start vertex through vertex c to get to vertex n. Okay? Does anyone want to see this in a kind of pictorial representation?
Yes, please.
All right, so let's go ahead and do that. Okay. So I'm going to start a new page to draw this picture. Okay. So once again, we got vertex S, the start vertex. We got vertex X over here, which is actually not important in this discussion. Okay, so vertex X is not even important. We have picked out a certain vertex C from the set O because, hey, it looks the most promising amongst all the vertices in O, and that's why we pick out vertex C. And we know vertex C goes to vertex N, okay, because that's what the for each loop is doing. And the this particular edge has d of Cn as its distance, okay. It is non-negative, but it has, otherwise it can be any value. And we know there's a path somewhere over here going from the start vertex to vertex C, and this is known as g of C, okay. G of C is the length of the shortest path from the start vertex to vertex C. So all of these are already given, okay. This is all we know, okay. So the question now is, well, this may not be the first time we get to vertex n, okay, and I'll explain later on why this may not be the first time we get to vertex n. In other words, we might have explored some other portions of the graph, and we already have a path from the start vertex to vertex n, and the length of that path is g of n, okay. So if I want to use a slightly different color here, okay, should have used a different color to begin with, but there we go. So the dark green one, I want to compare the dark green alternative to the orange alternative over here. I'm asking, is the orange path, which is what I have just found, is that any shorter? Is the length of that path shorter than the dark green one? That is what I'm asking, okay? Because if it is, then we probably have a few things to update. Does that make sense to all of you?
Yeah.
Okay, excellent. So switching back to the algorithm, okay? So that's why we're comparing, okay? And if the length of the orange path, which is here, is in fact less than the length of the dark green path, then we have just discovered a shorter path. So the first thing we do is we put n into the set big O, okay? So if I switch back into the pictorial representation, then we're basically, if the green line is shorter than the dark, the other way around, if the orange line is shorter than the dark green line, then we basically say, hey, this node here just has its values updated, okay? And if it is having its values updated, then all the vertices that are immediately connected to n, basically quote unquote downstream from n, they probably need to be re-examined, okay? Or examined the first time or re-examined. Does that make sense to you? Because n has its own vertices that it connects to, right? The blue line is representing all the outgoing edges from n. So if we just update the length of the shortest path from the start vertex to n, I probably want to touch the vertices that n is going to, because the length of the shortest path to those vertices may be affected as a result. Does that make sense?
Yes, that makes sense.
Oh, okay, excellent. So that is why we perform the step that is highlighted in the browser. We put n into the set O, to remind ourselves later on and go like, hey, we might want to check out vertex n now, in the future. Okay, so that's what we're doing. Moving on to the next line. So this line over here is to update the back pointer. In other words, if we have this entire thing solved, okay, we basically will start with the destination vertex and then look up its previous, and then we look up the previous of that, and then we look at the previous of that until we track our way all the way back to the start vertex. So every time we say, hey, we just found a shorter path from the start vertex to this vertex, we have to remember how to get back from vertex n to vertex c. So if I switch back to the graph here, okay, this is the edge that we want to remember, okay? But instead of remembering this edge in E prime or something like that, we just basically say, hey, to get to vertex n, the shortest path to get to vertex n is now vertex c. Now, it might be undefined earlier, okay? It might be somewhere else. I don't care, okay? I'm just saying that from now on, to get to vertex n, we're coming from vertex c, because that is the currently known shortest path, or it's along the shortest path to vertex n. Is that okay?
Sounds good.
All right, excellent. Thank you. Thank you for the confirmation. So that explains, the highlighted statement in the algorithm so far. And the next one is not really surprising. The next two lines are actually pretty easy to understand. The first one is, hey, we just found a shorter path, so we want to update the length of the known shortest path to vertex n to t, because that's what t is really representing. Okay, so that's not surprising. But if you update g of n, you probably want to update f of n as well, because f of n has a g of n component, so f of n also needs to be recomputed because of this. Okay, and that's all we do for each loop, okay, which is the in the loop in the A star algorithm. Okay, so we keep doing this until either O is empty, okay, or until every single vertex in O has an f value that is greater than or equal to g of x, because in that case we know, even if we were to go through every single vertex in O, we won't find a shorter path anymore. So are we still doing okay so far with the A star algorithm? All right. Cool. So there's a little bit left, okay, in the algorithm, which is basically how we define, the solution graph. Now the solution graph is no longer just G prime, it's G with a suffix of Sx. So the suffix Sx is indicating that we are starting from vertex S and we're ending at vertex X. Okay, we start with S, we end with X. It is a graph, so it needs a set of vertices. So we just reuse the same set of vertices as the original graph. But ESX is a little bit different. Okay, so we construct ESX using the following statement here. We basically go through every single vertex W in V, okay, and then we say if the previous of W is not undefined and instead it is vertex V, then we put the edge VW in ESX. So we're basically using all the previous, the back pointers. We're using all the back pointers to reconstruct all the edges in the solution graph. Now, this process can actually put in some edges that are not a part of the shortest path. That's okay. Okay, it's not a problem, because as long as we start with the destination vertex, and then we follow the previous pointer back to the start vertex, that path is going to be the shortest path. Okay, so we will put in some extra edges that is not a part of the solution, but it's okay. It doesn't really interfere with what we're trying to do, which is finding the shortest path from the start vertex to the destination vertex. So that's it. That's the whole algorithm. Do we have any questions before we move on to look at an example? because I think it is really important not to only focus on the symbols that we use in the expression of the algorithm, but also understand the meanings behind all the symbols. What is O, what is F, what is G, what is T, what is previous, and so on. So if there are any questions about what a particular symbol is representing, now is a good time to ask before we actually run the trace for this particular algorithm.
I suppose I could use a refresher of what prev is.
Prev? So
Yeah.
prev is basically just a back pointer. If we want to define a prev as a function, okay, so prev defined as a function is going to have a domain of all the vertices. Okay, so that's the domain, but the codomain is not going to be all the vertices, because all the vertices does not include the undefined value. So the codomain is actually the union of V and the singleton set of something that we say undefined. Okay, that is a function. Okay, V is a function that can be described as mapping the domain, which is all the vertices, to a codomain, which is the set of all the vertices plus the undefined value, because that's how we initialize the previous for all of those vertices to begin with. Okay, so what previous is doing, the purpose of previous is to keep track of how do I get to a particular vertex? What is immediately before a particular vertex along the shortest path from the start vertex to the destination vertex? That is the purpose of prev, or the previous function. Is that kind of explaining? Okay, cool.
Yeah.
All right.
Thank you.
Excellent. You're welcome. Any other questions? All right, so if there are no questions, oh, somebody might have a question. Nope. All right, okay. So don't hesitate to ask if you have a question, but if I assume there are no questions at this point, let's go ahead and look at the graph and try to figure out, how A star would apply in this case. Okay, so I'm going to avoid the use of well, I suppose I don't have to do that. So we have a start vertex S and an end vertex X over here, okay? And I mean, we can try a graph that is just really simple, like a linear graph where there's only one path between S and X, okay? But that's not going to be very interesting because it won't show you how the heuristic works, okay? So we want something that at least has two alternatives, where it will find the destination and then it will go like, that doesn't, something looks kind of more promising. Let's try again, okay? So let's go ahead and construct the simplest graph that would do that, okay? So we'll have two additional vertices. One is vertex A and one is vertex B, okay? So the start vertex connects to vertex A, the start vertex also connects to vertex B. Vertex A goes to the destination vertex, vertex B goes to the destination vertex as well, okay? So the key is we are trying to design something to trick the A star algorithm and go like, yep, I'm gonna send you the wrong way, okay? And we want to see if the A star algorithm will understand it. Uh-oh, I just got tricked. This is not the right way to do it, okay? So we'll make one path, kind of not so attractive, having a this edge from S to A has a distance of 10. This one looks a lot more attractive. It only has a distance of 1. And then we pay for it later, okay? Whereas the other one, not too bad, okay? Just like that. Now, when you look at this, the Dijkstra's algorithm can work with all this information already. But the A star algorithm cannot, because the A star algorithm also needs to have the heuristic function defined. So now we need to define the heuristic functions. Okay, so first of all, let's go ahead and define AX. Okay, so HAX is going to be defined here. Now remember, the heuristic function is supposed to be very easy to compute, and it gives you a quote-unquote realistic estimate from a particular vertex, or the length between one particular vertex and another vertex. But nothing says that you cannot doctor the definition of H to trick the A star algorithm, which is what I'm doing here. Okay, so I'm totally doctoring, totally just making something to trick the A star algorithm here. So I'm going to make H of AX as large as possible. Let's make it a 10. Okay, we know that it cannot exceed 10 because the heuristic function is not supposed to overestimate the shortest path between two vertices. In this case, we know the shortest path between A and X has got to be just 10, right? The length of that shortest path has got to be 10 because that's the only edge between these two vertices. Okay, and then we'll define something between B and X. This is also just a heuristic function, and this time we are totally underestimating. We just say, well, let's just make this 0. Okay, it is legitimate. Okay, there's nothing wrong with these heuristic values at all. Okay, just in case someone is wondering, okay, it will never really happen, but the heuristic function of x to x has got to be 0. It cannot be anything else because the destination vertex is already at the destination vertex, and we know the heuristic cannot overestimate. So h of xx has got to be 0. Okay, but that's not very interesting. The heuristic of s to x is not really important at all. Okay, it's only here to initialize f of s. Okay, but f of s is not really useful. Okay, because the f value is useful only because when there are several things in O, we want to evaluate which one to use. So in this case, HSX is never really useful because the start vertex S in O is the only choice at the beginning of the entire algorithm. So it can be anything. It doesn't really matter what it looks like. Okay, so for this one, we can just make it kind of like, let's just make it 10. Okay, because it can go all the way from 0, which is the one extreme of underestimating the distance from S to X, or it can go all the way to 20, which is the length of the actual shortest path from S to X. Okay, so 10 is just somewhere in between, but as I said, it doesn't really matter. Okay, so do we have any questions about the setup of this example? Okay, no questions. All right, so I'm going to try to find a way so that we can look at all of this stuff here. So maybe what I'll do is this. Okay, I made the graph a little bit bigger than it needs to, so I'm just going to consolidate everything to use as little space as possible, so this way I can find a way to place these things in a sensible way. So we have, let's go back. Okay, so we'll start with the start vertex, A, B, X. This is 10, this is 10, this is 1, and this is 100. So this is all I need to display to get this to work. And I certainly don't need all the decorations and whatnot here. So what I'll do is I'm going to take a screenshot of this portion and then use a much smaller window to display it. So give me a second to set this up, like so, and then open it with fair. Okay, there we go. And now we can, so I want you guys to open up your own browser so we can look at the algorithm, because I'm going to move this off the screen so that I can look at it too. And then just like last time, I'm going to use a spreadsheet to keep track of a trace of how things are initialized. So we'll go ahead and go to Office and then go to Calc, like so. All right. So I'm going to have to move things around just a little bit here. All so that looks good. And this one is on the side, not interfering in any way with the spreadsheet. Okay. All right, so there we go. All right. So let's go ahead and keep track of what we need to track. Okay, so S and X do not need to be tracked because S is the start vertex, X is the destination vertex. So they are not variables. I'm not going to waste a column on those things. We know O is a set. Okay, so we need to keep track of O as a set. In the algorithm itself, it uses local variable C to keep track of which vertex am I picking out of O to explore. So C is a variable that we need to keep track of. We need T because T is computing the length of a path from C to N. Okay, so we need N first. Okay, so we need N. And then we have local variable T. And then we have all the functions. Okay, so we got two functions. We got function F, function G first. So with function G, we have got four vertices. We got vertex S, vertex A, vertex B, and then vertex X. Okay, so I'm just gonna consolidate, not consolidate so much, but to at least make these a little bit narrower. And then we got function F, which also has S, A, B, X. And then once again, we meant to do a shift click. And then we make these a little bit narrower because we have previous as well. So previous also has S, A, B, X. And these, I suppose we can make them as almost just as short because we just need enough space to say undefined, which is just UND for undefined. Okay. So the initialization would assign a 0 for G, and then for the F value, okay, let me just kind of do a little bit more over here, so this way we can it's easier for us to see which columns belong together, like that. Okay, and we can even do a little bit of color coding. Okay, with this light orange, a light yellow, make this light green, and then with this light blue. There we go. Okay. So the initialization would say f of s is just h of sx, which we know as 10, and then everything else is infinity, okay, as large as possible. So this is how we initialize g and f as functions. And then for prev, or the previous, everything is undefined. So I'll just use UND for undefined. Okay, there we go. All right, so when we start the algorithm, we initialize the set O to just the start vertex. So it's just a set with S as its only element in it. So now we are ready to run the algorithm. And I think we can make these a little bit narrower as well, just like that. There we go. All right, cool. All right, so we are now running the algorithm. So we are now getting to the while loop part. Okay, so the while loop is going to look at the set and is asking the question, and it asks, can I find at least one vertex in O such that the f value of that is less than the g value of x, okay? So there's only one vertex here, but I still have to answer the question, is the f value of s less than the g value of x? So we look at the g value of x, it is infinity. We look up the f value of s, it is 10. 10 is less than infinity is true. So we have to get into the while loop to perform at least one iteration. On the line right below the while statement, it says let C in O such that, basically C has the smallest f value of all the vertices in O. Well, guess what? There's only one vertex in O, so I don't really have to do anything to find the minimum, because the only element has got to be the one that I can choose because it's the only one. So C is now the start vertex S, okay? And then we have to remember to update the set O, so it's now empty. So now we are moving down to another line, the for each loop inside the algorithm. So what the for each loop is doing is it's looking into all the outgoing edges of the vertex that is now in variable C. So it's got two outgoing vertices. One is SA and the other one is SB. It doesn't really matter which one you explore first. Okay, so in the for each loop, you can just randomly pick which one to go first. It doesn't really matter. So we are just going to say, let's go ahead and explore SA first. Okay. Now, if we explore SA, then we have to compute T. In the algorithm, which is the one line right below the for each line, it tells us how to compute T. Okay, it says, take G of C and then add D of Cn to it, and that becomes our T. Now, vertex C, or C as a variable, is storing S as its vertex, and G of S is 0. And then D of Cn, which is the distance of the edge from S to A, is 10. 0 plus 10 is just 10, so T is now 10 over here. And then we move down to the conditional statement. Okay, we are now asking, is 10 less than G of n? N is A, so G of A is currently infinity. 10 is less than infinity is true. So now we have to get into the then branch of the conditional statement. The very first thing it does is to add this new vertex A to set O. So O is now having a single element of A at this point. The next thing it does is to keep track of the previous. So the previous of vertex A is no longer undefined. Instead, it is vertex S. And then the line below that updates G of n. So G of A is now updated to 10. And then the line below that is adding H of nx, which is AX, to G of n. And according to this, H of AX is 10. 10 plus 10 is 20. So f of A is now updated to 20. Do we have any questions about the first iteration of the for each loop when we look at neighbor A of the start vertex S? Okay, so looks like that's good so far. So now we ask the question, is there another vertex that S has an edge to go out to? And the answer is yes, okay, because S here goes to vertex A, but it also goes to vertex B. So now we say, well, let's consider that neighbor, that outgoing neighbor of S, okay, vertex B. And just like before, we have to compute T. And in the algorithm, T is G of C plus D of Cn. G of C, which is G of S, is 0. And then the edge going from S to B has a distance of 1. 0 plus 1 is 1. So T is 1 over here. And then we ask, is T less than G of n? Okay. G of n, once again, is G of B. G of B is currently infinity. And T is 1. 1 is less than infinity. Infinity is true. So we get into the then branch of the conditional statement. The first thing it does is to add vertex B to the set O. So now O has two elements, A and B. The second thing it does is to keep track of the previous of B. So now B also has a previous of S. So at this point, okay, you can see how the algorithm is saying, yeah, we can go from S to A, but we can also go from S to B, okay? But that's not a problem, okay? We'll see why that is not a problem later. And then we assign t to g of n. T is 1, and then we update g of n, which is g of b, to that value, which is 1. And then we also have to update f of b. And f of b is the tricky part, okay? Because it is g of n, which is g of b, which is 1, plus the heuristic value going from b to x. But we can see how we totally doctored h of bx to be just 0 when the actual cost of h has a distance of 100. I'm estimating it to be 0, okay? But that's legitimate because anything that is not overestimating and not negative is fine, okay? So the f value of b is unrealistically a 1 at this point, okay? Because remember, I was trying to trick the algorithm to follow the wrong path, okay, and see if it can recover from choosing the wrong path to begin with, right? So do we have any questions at this point? Because we are done with the second iteration of the for each loop. We have now completely explored all the neighbors that vertex as the start vertex can reach, which are basically vertex A and B, vertices A and B. So do we have any questions at this point? No questions? All right. So now we are going back to the while loop, okay, going back to the while condition. So if you're reading the algorithm, the while condition says, okay, does it look promising at this point? Okay, does it look like we still got work to do? Okay, we just want to find at least one vertex in O so that the f value of that is less than the g value of x. So we look at the g value of x. G of x is still infinity. And then we look at the f value of a and b. One is 20, the other one is 1. Well, I mean, definitely less than infinity. So we are now going to perform another iteration of the while loop. First thing in the while loop is let's pick a vertex in O so that it is the one that has the least f value. Now, in the previous iteration, it wasn't a big deal because s was the only element in O at the time, so there's nothing to compare to. But this time we got 2 elements in O, and now we have to say, okay, which one looks the most promising? And the f value basically is how we evaluate whether a particular vertex is promising or not. F of A is 20, f of B is 1. I mean, I'm going to pick B. B looks so much more promising at this point. So we choose vertex B out of O, and that becomes our C at this point. And then we also have to remember to remove it from the set O. And now we ask, well, does it have any outgoing edges? In other words, can we go from B to somewhere else? The answer is yes. Okay, so let's look at the vertex B over here. It can go to the destination. So seemingly, we are pretty much close to done, right? Because there's an edge going from B to X over here. And now we have to compute T. So T is G of B, in this case, which is a 1, okay, plus the distance of the edge going from B to X. The edge going from B to X has a distance of 100. So it's 1 plus 100. So T is 100 over here. So, excuse me, 101. Okay, I cannot add. So it's 101. So now we are asking in the algorithm, the next thing we do is the conditional statement, the if statement. The if statement is comparing T, which is 101, with G of n. N is x, so we're comparing to G of x. G of x is still infinity at this point. 101 is less than infinity is true. So we go into the then branch again. So when we get to the then branch, the first thing we do is we add x to the set O. So now the set has both A and X as elements in it. The second thing is to update the previous. Okay, so the previous of X is now B. Okay, so it looks, okay, wrong row. Okay, let me see which row we should be in. There we go. So it is the correct row. Never mind. Okay, but the confusing part is Isn't that wrong? Because this is not really the shortest path. Okay. Well, but it is the first path that we have found to vertex X. Okay, it is the first path, just not the shortest one. Okay, so we'll find out later on how this is all going to be fixed up. Okay. So we are moving on to the third line after under the if statement. It updates g of n to t. N is x, so g of x is now updated to 101. And then we also want to update f of n, okay, which is over here, to g of x plus the heuristic going from x to x. The heuristic to go from x to x has got to be 0 because it's the same vertex. So it is 101 as well for f of x. Okay. Do we have any questions at this point? No questions? All right. All right, so at this point, we are done with the for each loop because from the perspective of vertex B, there's only one outgoing edge to vertex X, and we have just explored that. So we are done with this while iteration of the while loop. We go all the way back to the beginning of the while loop, and then we look at AX, and then we ask that question again, okay? Have we found the shortest path? So this time is a little bit tricky because g of x is not infinity anymore. You cannot just say, well, since g of x is infinity, of course we have a shorter, there's a possibility to find a shorter path. Well, g of x is not infinity anymore. It is 101. So now we really have to look at the f value of both a and x, okay? So the f value of a is 20. The f value of x itself is 101. Is one of these two less than 101, which is g of x? The answer is yes, okay? F of a is less than g of x, so we have another iteration of the while loop to perform at this point. So we get into another iteration of the while loop, and this time we have to once again choose between two possible vertices in O, and it's between a and x in this case, and we have to choose the one that has the least f value. F of a is 20, f of x is 101, and so the one that we should choose is a because it has the smaller f value. So now we say, okay, let's pick a out of the set. So now the set O only has x remaining in it, okay? And now we look at all the outgoing edges from A. And we can see that A only has one outgoing edge, and it is 2x. So n is now x. N is x is correct. And now we have to compute t. T is g of c plus d of cn. So g of c is g of a is 10, and then the distance of the edge going from a to x has a distance of 10 as well. So 10 plus 10 is 20. T is now getting a value of 20. Then we use the value of t and compare it to g of n. N is x, g of n at this point is 101. 20 is less than 101, so we are now getting into the then branch of the conditional statement. So in the conditional statement, the first thing we do is we add x to the set O, but since the set already has x in it, so it doesn't appear to have changed because we cannot have duplicate elements in a set. And then the next thing we do is to keep track of the previous. Now this part is important because this is where we go to the previous of x and go like, well, guess what? Erase what we put here to begin with. It is now a. This is how we can recover later on, after discovering a path to the destination, and then later on figure out, no, that was not the shortest, okay? So this is how we can basically refine our answer and go like, yep, there's a shorter answer here. There's a shorter path, okay? And then after that, we update g of n. So g of n is g of x. It is now going from 101 to 20. And then we also have to update f of n, which is 20 plus 0. So that's just 20. so that is the end of the for each loop inside the while loop, because from the perspective of vertex A, it only has one outgoing edge going to vertex X. So that's why we only got one iteration for the for each loop. And then we go back to the main while loop now. So in the main while loop, okay, we look at, well, it only has one vertex in O, but we still have to ask the question, okay, which is there anything in O at this point where the f value is less than g of x? Well, the only vertex in O is x itself, so we look up the f value of x. F of x is 20, and then we compare it to g of x, which is also 20. Well, 20 is not less than 20, right? So that means no, we cannot find any vertex in O where its f value is less than g of x. So that makes the condition of the while loop false, which means we're done. We now get out of the loop. We are done with tracing this algorithm at this point. Do we have any questions at this point? No questions? Okay. So we are not entirely done with the algorithm because we still have to kind of follow the previous pointers. So I can just kind of display this on the side because I think there's enough space to show these side by side. Well, maybe not side by side. Let me see if this works. Yeah, that'll work. There we go. Okay, so we're gonna draw the rest of the picture. Okay, so now we look at define GSX blah blah blah. Okay, so we just want to figure out what edges are in ESX. So we just basically follow all the previous. The previous of S is unknown, so it doesn't correspond to a particular edge. The previous of A is S. Okay, so let me use the red color here. So this edge is now a part of ESX. Then we look at the previous of B, which is also S. Okay, so this is also a part of ESX. And then we look at the most important one is the previous of X, which was B, and then we updated it to A. So that means this is also a part of ESX. Okay. So it is correct. Okay. So you're correct that we got an extra edge here that is not on the shortest path from S to X. That is correct. Okay. The edge going from S to B is not really a part of the shortest path. But if you start with the destination vertex, which is X, okay, if you start with X here, you follow the previous to A, and then you follow that previous to S, that becomes the shortest path from vertex S to vertex X. Do we have any questions about the algorithm? Because now we're done, tracing it for a very simple example, but even this particular example illustrates, why, how it works. Okay, you basically, yes, you can set up the heuristic so that it tricks the algorithm into exploring a path and even finding a path to the destination that was not the shortest, but the algorithm is not going to stop until it is convinced that it has found the shortest path. So do we have any questions about this trace? Because I think the trace itself is kind of important, okay, because it gives you the hands-on experience of working with this. Are there any questions? I'm not hearing any questions, and we are out of time. We are out of time by 5 minutes already. Darn it. Okay, so what I'll do is I'm going to give you guys a graph so they can solve the shortest path using both Dijkstra's algorithm and also using the A-star algorithm. Okay, so this way, you guys actually get something to work on, and I would advise you to use the same trace mechanism that I use here, and also the trace mechanism that I used in the previous class for Dijkstra's algorithm. Okay, because this way it really helps you to kind of keep track of what am I doing here, which vertex am I exploring, which neighbor of that vertex am I exploring, should I update, what should I update that value to, and so on. So I personally find that this is one of the easier way for myself to keep track of the values of variables as I go through A-star and Dijkstra's algorithm. So that's definitely something that I will get you guys to do, by constructing a graph, and I'll probably post it over here in Discord, but I'll send a notification on the side of Canvas so that people who did not get to Discord will also know about that. So that's definitely one thing that I'll do. And then the second thing is, if you feel that you want to kind of implement all of these algorithms on your own, it's not a bad idea if you have the time. Okay, so that's kind of important because we are close to the end of the semester, and I think most of you are not just taking this one single class, so I do understand it. Yes, I'm going to pin the spreadsheet and also the Zernal document. So give me a little bit of time to export that first. Okay, I'm going to put this into the temp folder, and then also save the spreadsheet to the temp folder. All right, so this is 2020-0504. May the force be with you. I'm kind of surprised that nobody mentioned that today. All right, so we have this. Let me see if I can upload two files at the same time. Oh, maybe not. Okay, trace of today. Okay, so it asks separately. Okay, pictures of today. There we go. And let me see if I can select both. Nope, I can only pin one at a time. So there's that one, and there's this one. There we go. So by tonight, if you do not receive an announcement from me about an example that you guys can use to practice on the algorithm, just send me a nudge, send me an email, or on Discord, just kind of nudge me and ask me about it, okay? Because I need a little bit of time to kind of construct an example that is simple and yet at the same time, it exercises all the different logic of the algorithms. So that will take just a little bit of time. Are there any questions I can answer before I get off of the live stream? No questions. All right, so if there are no questions, I'm going to stop the YouTube recording, and then I'll stop the live stream over here and also the voice.